Hi. So what I want to do in this video is one of the examples from the review packet that I put out on Canvas. And that is this example here where I give you a pendulum of length L. You can see that that's the length of the pendulum. And this pendulum has a point mass, N, the point mass, at the top of it. And it is held up by two springs, or rather it's attached to two springs, where you have this spring K1 that is H1 up from the ground, and then you have this second spring K2 that is H2 up from the ground. And the goal for this problem is to try to find a natural frequency using Euler's second law. Now, we know Newton's second law is F equals ma. Euler's second law looks very similar. This says that instead of summing forces, we sum moments about some point. That will be equal to, instead of ma, it's equal to j, the mass moment of inertia, about that point times the angular acceleration as opposed to the linear acceleration. So this kind of looks like F equals mx double dot. It's have the same type of form. So that is what we want to do for this problem, and we have to choose a point that is convenient for us. And for this type of thing, if you're thinking about the free body diagram ahead of time, we know we have forces due to these springs. We know we have the mass that contributes a force, but then there's also some sort of force that's in the rod. That's some sort of tension. We also know that there's some reaction forces due to the pin, and ideally we just cancel all those out. So we want to pick a point such that the moments that are created by those forces are zero. So basically they don't cause any rotation. So the convenient point to pick is the pin, because at that location, if I were to draw some force, let's say horizontally, I'll do it in a different color. If I were to draw some force, let's say I'll do vertically instead, it's easier. This cannot rotate the pin. It's going through the pin. It'd be like if you tried to crack your knuckle, and I can like bend on it. If I tried to crack my knuckle just pulling on it, there's no rotation. There's no force that is causing it to want to turn. So we want to pick that point. So we'll sum the moments about point O. And what our responsibility is to now find what those moments are, find what the mass moment of inertia is relative to point O, and then we will be able to derive our differential equation. And from that differential equation, we can find the natural frequency. So what I like to do is draw a picture where this thing is now deflected some, and I'll draw it very exaggerated. So here's my ball. And let's say it is going to the right. Again, it doesn't matter which way you choose. You just have to be aware of what direction is positive. And at that position, I'll say that it's going clockwise. So what forces are acting? Well, we have gravity. There's gravity in the problem. Otherwise, it wouldn't move. So we have, I'm going to make this ball black, actually, just so it is easier to see. Let's go ahead and we'll have some mg that is pointing down. And again, relative to this point O, that is going to cause it to turn and spin relative to point O, in theory. So that's why it contributes a moment. In this situation, where I have this thing now to the right, what is happening with K2? Are we stretching or are we compressing it? Well, if it's moving to the right, we're going to say that K2 has shrunk a little bit, so it's being compressed. And they don't like to be compressed. They would rather be in equilibrium, so that's going to cause a force acting in this direction. That will be K2, and I'll just say X2. We don't know what that is right now, but we'll just leave it like that. And then K1 in this situation is being stretched. So you might think it's the opposite of what we just did for K2. But again, springs want to be in equilibrium. So if I pull on it, it says, no, I don't want to be in that direction. So that force is also going to act to the right, K1, X1. And then, of course, we had all these forces that were here that we're going to neglect because they go through the pin. They don't cause a moment about that point. And those are the things we care about. So those are our moments. And now we need to figure out what those moments are, or those are our forces. Now we need to figure out what the moments are based on the moment arms. Basically, we need to look at the perpendicular distance to the force. So again, it is dropped by some angle theta. And I am interested in knowing what is, let's say, the perpendicular distance to each of those forces. So I'll go ahead and maybe I'll do a different color here. I'll draw that to help us. And let's first look at the mass. So if you look at the mass, this is the moment arm for the mass. That's the perpendicular distance of the force. And I have this giant right triangle here where the length of the hypotenuse is L. That means that this is going to be L sine theta. Now, is the mass helping or reducing? I don't want to say helping. Is the mass causing clockwise rotation or stopping it or minimizing it? Well, we see that this arrow wants to go like this, which is exactly what the angle is doing. The mass wants it to go clockwise, which makes sense. Gravity's acting downwards. It wants this thing to fall. So that means from mg, I'll say the moment of mg, this is going to be mg, that's the force, multiplied by the moment arm, which is L sine theta. So that is one moment we need to keep in mind. Now, let's look at, let's say, the force from K2. Similarly, we want to find the moment arm, so I'm going to draw, again, a right triangle. I'm going to draw it at this location, though. Because we want to see what that moment arm is. So for this force that's acting horizontally, we need to find the perpendicular distance, which would be this guy. Because again, the force is acting to the left. We need the moment arm to be up or down. So a part of this triangle, if you look here, that length is going to be H2, which means that this is going to be H2 cosine theta. And is this causing rotation, helping the clockwise rotation, or is it limiting it or stopping it? And we see that this is trying to, about this pin, it's trying to go this way. This is acting opposite the motion. It's trying to restrict it. So this is going to be a negative moment. So M of K2, X2, this is going to be the force, K2, X2, multiplied by the moment arm, which is H2 cosine of theta, with a negative sign. And again, we'll have to deal with the fact that we have x's later on because x is not a defined variable in the problem. We want our differential equation to be in terms of theta because this object is rotating. It's not translating. It's just spinning around the pivot point. And then similarly, if we did this again, go ahead and erase this stuff. If we did this again, but now I'm looking at K1, it's the same type of deal as K2, except the only difference is now the moment arm is going to be, and if you come back to the problem, that's H1 cosine theta. So that means that the moment of K1, X1 is, again, it's going to be negative because of the fact it's trying to impede the motion. So now I have these three moments. And at the end of the day, I want them all in terms of theta. So right now, this is good, and these two need to be fixed. So we need to figure out what x2 is. So if we're looking at this picture again, x2 is this distance right here. This is x2 that I just drew in black. That's how much the spring is compressing. That's going to be based on the right triangle where h2 is the hypotenuse. This is h2 sine theta. And similarly, x1 is going to be h1 sine theta. So those will be plugged into my equation for the moments. So now we have found all the moments. We're going to sum the moments about that point, set that equal to j naught theta double dot. It's going to be mgl sine of theta minus k2 x2, which is h2 sine of theta, times h2 cosine of theta. Remember, that's the moment arm here at the top. Minus k1 x1 is h1 sine of theta times h1 cosine of theta. Again, that's the moment arm. And this whole thing's going to equal j naught theta double dot. But now I need to find j naught. So j naught, this is some arbitrary point. It is not located at the center of mass of the system, so we have to use the parallel axis theorem. Which says that the mass moment of inertia about any point is going to be the mass moment of inertia about the center of mass plus that mass times how far away that mass is from the point O. So again, in this problem, we have this pendulum where this is the only mass in the system. And I told you that it is a point mass. A point mass has no distribution of mass about its center. It's basically just a dot. So just like a dot, basically. You can see the little dots I'm drawing. Now, because of that, that means that the mass moment of inertia is equal to 0, about the center of mass. Because there's no resistance to rotation. It's just a dot. It's not going to rotate or spin about its axis. So we say that J naught is going to be equal to M, and then the distance from O in this problem is L. So that's ML squared. So I'm just going to copy and paste this down. So if we have that now, that means that this J naught over here is ML squared. So we get ML squared theta double dot. Now we have a differential equation set up where it is nonlinear. This is nonlinear, which we know is gross. We would much rather have it be linear. So to linearize, we used a small angle approximation, basically saying that the angles in this problem will be tiny. And if we have a linear differential equation, that's easier to solve. So let's look at the small angle approximation. If we have sine of theta, we're going to say that that is approximately equal to theta for small angles. Where does that come from? Well, if you do the Taylor series of sine of theta, that's theta minus theta cubed over 3 factorial, theta to the 5th over 5 factorial, etc. And if the angle's small, we will neglect those terms, which will lead to just sine of theta being theta. From a unit circle perspective, if I draw a unit circle and I have a tiny angle theta, this is theta. This is the distance above the x-axis. this ends up being approximately equal to theta when that theta is very tiny. This picture will become important in a second when we look at cosine. Cosine of theta is approximately equal to, well, let's come over to this picture. Cosine is the horizontal component, which if theta is very small, this will be approximately equal to 1. Because cosine of 0 is 1. So that means if theta is small, that'll conclude that our cosine of that small angle is approximately 1. And again, if we look at the Taylor series of cosine of theta, this is theta minus theta squared over 2 factorial plus theta to the 4th over, sorry, not theta, 1. Etc. And if theta is small, we'll neglect those terms, which tells us that cosine of theta is 1. So coming up here, what does that tell us? Well, this means that this term here is going to become theta. That's going to become theta. That's going to become 1. Theta and 1, which simplifies things a lot. So let's go ahead and copy and paste this so we can view it down below and rewrite it. So this is going to be mgl theta minus k2. We have h2 twice, so that'll be h2 squared with the theta, minus k1, h1 squared with the theta. That is equal to ml squared theta double dot. And I can bring everything over to one side and then divide by ml squared if I want. So if I bring this over, it's going to become positive. That's going to become positive. That's going to become negative. And dividing by ml squared, I'll get theta double dot plus, and each of these terms has a theta, so I'll factor it out. This is going to be k2 h2 squared over ml squared plus k1 h1 squared over ml squared minus mgl over ml squared times theta is equal to 0. I'm going to double check my work to make sure that that's correct. And it seems correct. Yeah. So that means that if we think back to our original differential equation in vibrations, this is the most important equation, or leads to the most important equation. If we turn it into monic form, we know that the coefficient that's in front of the x or in front of the theta, that's going to be omega n squared. So what that reveals is that omega n is the square root of k2 h2 squared plus k1 h1 squared plus, or sorry, minus mgl over ml squared. And that is our answer for the problem using Euler's second law. Now, what's interesting about this is that you see that depending on the length, or really depending on this length, because that term ends up, that L cancels one of those L's, depending on the combination of length and gravity and what those stiffnesses are in their distances, it is possible that the square root inside ends up being negative, which means we would end up with an imaginary frequency. Now, that's not physical. That is a limit for our problem. We see that we have an inverted pendulum. What will happen at some point? If this thing moves too far, what happens? Well, ultimately, the gravity in the problem will overpower the spring forces and the thing will just collapse. That's when the problem ends. So if you ever end up with a negative frequency in here, we're no longer stable and our system will just destroy itself and fall. I hope this makes sense. If it doesn't, please let me know. Otherwise, we'll see you in a future video. Thanks. Bye.